Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on August 21st, 2025, about 4 days ago. The headline result is a neural dynamics model that slots into a standard robot simulator, replacing the low-level dynamics and contact solvers, and it stays stable and accurate over hundreds to 1,000 steps, while generalizing across tasks and environments. The paper is titled Neural Robot Dynamics, and as we will see later, the implications for training and deployment are quite significant. Beyond stability, the model supports zero-shot policy transfer, fast fine-tuning with real data, and practical sim to real performance gains. Alright, the tweets highlight a neural simulator that replaces low-level solvers, predicts dynamics accurately, generalizes across tasks, and adapts to real data, with one post drawing strong engagement at 110 likes. Earlier, the social chatter focused on broad takeaways. Figure 1 presents the 6 robotic systems that ground the claims, which matters because the range stresses generalization across contacts and controllers. The panels span cart pole, double pendulum, ant, Franca arm manipulating a ball, animal quadruped, and a cube toss scene. The lineup signals that one learned dynamics backend aims to handle both classic benchmarks and contact-rich manipulation across long horizons. Alright. The previous figure set the robot lineup, and figure 2 shows how the method plugs into a simulator. The top panel contrasts a classical workflow that feeds intermediate quantities to a physics solver, which motivates replacing only that solver. The middle panel presents the hybrid path, where a learned module predicts the next relative state from robot state, joint torques, contacts, and gravity in the robot frame. The right panel illustrates the robot-centric representation, which stays invariant to global shifts, so the model trains more efficiently. Okay, the previous figure outlined the hybrid solver. Figure 3 shows long horizon accuracy for passive motions, with a table at left and a trajectory plot at right. The table reports tiny errors, which stay small even at 1,000 steps for cart pole, and at 500 steps for ant. The right plot overlays ground truth and model trajectories for cart pole, and the curves align closely over 1,000 steps, so drift remains limited. Alright. The previous figure highlighted long horizon accuracy. Table 1 now reports policy rewards, which compare training and evaluation inside the neural simulator versus the ground truth engine. The numbers stay closely matched across cart pole swing up, Franca reach, 3 ant tasks, and 2 animal velocity trackers, so policy behavior transfers with minimal loss. The largest positive gap appears in ant running at about 17%, while differences for animal are near zero. This table presents strong evidence that policies trained entirely in the neural backend deploy reliably elsewhere. Table 1 had shown close policy rewards across engines. Figure 5 presents fine-tuning on real cube tossing, which demonstrates that pre-training and simulation, and then adapting to real data, yields lower errors and faster convergence. The left and middle panels depict trajectories with light green ground truth frames, so visual alignment is clearer. The right plots show position and orientation errors dropping quickly for the fine-tuned model, while training from scratch decreases more slowly. The dashed line marks the warp baseline error. So, stepping back, 2 takeaways stand out. Swapping only the dynamics and contact solver with a learned module delivers long horizon stability and strong policy transfer, and the robot-centric, spatially invariant state enables efficient training plus fast sim to real fine-tuning. Spatially invariant means predictions do not change under global shifts. Thanks for listening. I am Alex, signing off.